Hello everyone and welcome back to the C++ 3D game tutorial series. In this 27th video tutorial, we will see how to make smooth camera movements. In particular, we will see how to use the lerp function to move and rotate our camera and spaceship smoothly. We will spawn hundreds of asteroids into our scene, and as last thing, we will exploit this feature to introduce visual feedbacks for the normal and turbo speed modes. As always, we will face three main parts: requirements, design, and implementation of all the necessary things to create smooth movements. So let's start with the requirements. We need a C++ IDE. Visual Studio is recommended. The target platform is Windows. We also need DirectX 11 SDK, and last but not least, a bit of knowledge of C++ programming language is recommended. Now we can start the design part. The last time we have seen how to make a third-person camera and how to move our spaceship through the usage of W and S keys. Today we will start exactly from there, making smooth all the current movements. How can we make the movements of our camera and spaceship smooth? By using an important math function we have already used during the series, the lerp or linear interpolation function. We know that the lerp function needs a start point, an end point, and the delta value that goes from 0 to 1. By changing the delta value from 0 to 1, the lerp function allows us to go from the start point to the end point linearly. But now, what are the points and values we have to pass to the lerp function in order to create smooth movements? We have to proceed in this way. We need to calculate and store two positions. One is the normal position we already have, whose movement is the following. Let's substitute the point with the spaceship. The other one that we can call follow position, it is a new point that follows the normal position, but delayed of some seconds, like in these images. Let's see how it looks with the spaceship model. The follow position, that is the black point, will be effectively the position we will use for our spaceship. But how can we calculate the follow position? We have to linear interpolate the follow position with the normal position, applying a specific delta value, and in the end the result will be saved in the follow position. The delta value should be calculated in such a way to delay the movement of the follow position of some seconds, creating in this way the smooth effect. At the end the results will be like this. Now the movements of the spaceship are smooth, but only from the position side. The same exact procedure can be applied even for the rotation of our spaceship, achieving this result. Very well. Unfortunately, we have some weird effects, mostly when we rotate our spaceship. This happens because we have created smooth movements only for the spaceship. In order to complete the job, we have to make smooth movements even for our camera. The procedure is the same that we have applied to the position and rotation of our spaceship. Very well. The next step to face is the spawning of hundreds of asteroids in a random way. To do that, we add three arrays of type vector 3D, where we store the positions, rotations, and scales of our asteroids. Once we have done this, we will compute position, rotation, and scale values randomly by using the rand function. To pick a random number inside a specific range in C++, we can use this formula, where max is the maximum value and min is the minimum value of the range. For example, if we want to pick a random number in a range between -2000 and 2000 for the position of an asteroid, the formula will become the following. At the end, once we have all the data we need, we will loop over our position, rotation, and scale arrays to render our asteroids, in the same way we have done for the other meshes. At the end, this will be the result. It's a bit slow though. We should add a sort of turbo mode. We can do this by adding a speed value attribute and multiplying it in the formula we have used in the previous tutorial to calculate the position of our spaceship. So far so good. We can also change the speed value at the pressing of Shift key in the on key down method. Unfortunately, even if we switch from a low speed to high speed and the other way around, we don't have a visual feedback of the switching. To provide this visual feedback, we can use the camera distance used in the previous tutorial to distantiate the camera from the spaceship. In the end, to provide a smooth transition, we will use again the lerp function for the camera distance value. And here is the final result. Very well, now we can start the implementation. As first thing, let's enlarge our skybox in order to have a big scene in which we can fly. Let's increase even the distance from the far plane. At this point, we can start to make smooth the translation movements. Let's go to App Window Header File, and here let's add a new Vector 3D attribute. Let's call it Current Spaceship Position. Now, let's come back and in the Update Spaceship, let's compute the follow position by using the lerp function. Now, let's go to Render method, and here let's substitute the spaceship position with the current spaceship position. As the last thing, let's go to Update Third Person Camera, and here let's assign the current spaceship position to camera position. In such a way the camera can follow the spaceship. And it works! Now the translation movements are smooth. At this point, let's make smooth even the rotation movements in the same exact way. So let's go to Header File, let's add the current spaceship rotation, and in the Update Spaceship method, let's use the lerp function in the same way we have done previously. Let's go to render method and let's place the current spaceship rotation. Let's see if it works. And it works, but as we have seen in the introduction, there are weird effects because the camera doesn't follow the spaceship movements smoothly. So let's go back again and let's make smooth even the camera movements in the same way we have done so far with the spaceship. Let's add the current camera rotation. Let's go to update third person camera and here let's calculate the position by using again the lerp function. Let's put the call to lerp function before the rotation matrix calculation. In such a way we can calculate the rotation matrix with the updated values. Let's apply the same thing even in the update spaceship method. Let's see if it works. And it works. Now the movements are completely smooth. Very well. Now we can start to spawn our asteroids. So, as we have already seen in the introduction, let's add in App Window Header file 3 vector 3D arrays of 200 elements, one for the position of our asteroids, one for the rotation, and the last one for the scales. Good! At this point, let's go to onCreate method, and here let's initialize all the values. So let's add our loop to loop over 200 elements, and let's start with the position. Here we have to see how to calculate a random number in C++. To do that, let's include the time header file. Before the loop just created, let's call the sRand function that initializes the random number generator. Then we can calculate the random number with this formula that we have seen in the introduction. In this case, we are calculating a position in the range minus 2000 and 2000. Let's do the same thing for the rotation. In this case, we are calculating a random rotation between 0 and 6.28 radians that corresponds to 0 and 360 degrees. Let's do the same thing for the scale. In this case, a scale between 1 and 9. Very well. We have initialized the transformation for our asteroids. And so, let's copy past this while loop cycle and let's go to render method. Here, let's pass the while loop and let's put the code we use to render the asteroid model. Obviously, let's pass our just calculated position, rotation and scales to the update model method. Before to proceed with the build, let's come back again to the onCreate method And here let's make the scale of our asteroids uniform in all the directions. Let's see if it works, and it works. Let's improve again the camera movements. Let's add a camera follow effect when the spaceship is moving forward or backwards. So let's add a current camera distance in a window header file. At this point, let's go to update third person camera, and here let's change the camera distance variable based on the forward movement. If there is no forward movement, then let's set a default distance of 14 units. If there is forward movement and it's positive, so the spaceship is moving effectively forward, let's increase the distance to 16 units. If instead the spaceship is moving backwards, let's decrease the distance to 9 units. Let's make the change applied to camera distance smooth by using again the lerp function. Unfortunately, we don't have a lerp function that accepts only numbers. So let's create a new header file and let's call it mathutils. Let's go to Vector3D class and let's copy paste the lerp function into the mathutils header file. At this point, let's adjust the function in order to accept only float numbers. Good. Let's go back to update third person camera, and here let's apply again the lerp function as we have already done previously. Let's see if it works. And it works. So far, so good. The next step to face is the implementation of turbo mode. So let's add a new boolean attribute and let's call it turbo mode. Now let's go to on key down and let's handle the pressing of shift key. When we press the shift key, we enable the turbo mode. At this point, let's go to on key up and here at the release of shift key, let's disable the turbo mode. Now we can go to update spaceship method and here let's handle the spaceship speed. Normally we set a speed of 125 units. If the turbo mode is enabled, instead we set a speed of 305 units. Good. At the end, let's go to update third person camera and when we are moving forward, let's check the turbo mode attribute. If the turbo mode is not enabled, let's do the same thing done previously. Otherwise, if turbo mode is enabled, if we are moving forward, let's set camera speed at 25 units, otherwise 5. Let's see if it works, and it works very well. Let's improve a bit the lighting, making it a bit more brighter. So let's go to directional light pixel shader and here let's set the Ka variable to 8.5. Now let's go to update method and here be sure to move the update spaceship and update third person camera on the top. That's because update skybox depends on the position of the camera. Let's see if it works. And it works. But the asteroids seems a bit small, so let's enlarge them a little bit. It seems fine now. But as we can notice, the game doesn't run completely smooth. That's because there is a problem with the computation of the delta time. So let's go to the render method, and here let's set the delta time as the division between 1 and 60. This is the time in seconds required by a single frame to be rendered, when we have 60 frames rendered at each second. Currently we are sure to render 60 frames per second because we have the vertical synchronization activated. We will deepen this topic in the next tutorials. And as we can see, now the game runs more smoothly. But unfortunately, we have another problem. Sometimes the camera rotates freely without moving the mouse. This happens because we have to reset the delta mouse variable calculated in on-mouse move. You can reset them after the frame has been rendered in the onUpdate method. This problem happens because we have to call the update method during the resize. So let's do it. Very well, now everything works fine. And that's all for now, folks. Today we have seen how to make smooth camera and spaceship movements, how to spawn hundreds of objects into the scene, and how to apply the turbo mode. I hope you enjoyed this video. See you soon. Thanks for watching.